Mount St. Helens erupted. 57 people were killed, and it triggered the largest landslide in recorded history.
Mount St. Helens is about to blow. It's all after the area saw hundreds of recent earthquakes.
45 years after Mount St. Helens devastated the Pacific Northwest, leveling forests, darkening skies, and scattering ash around the world, the mountain is whispering its warnings once again. But this time, the message isn't a plume of smoke or a ground-shaking roar. This time, it's heat, strange, persistent, and focused deep within the caldera itself. May 18th, 2025 marked the eruptiversary of the infamous day in 1980 when the mountain's north flank crumbled in an instant and 57 lives were lost to the violence of molten rock and choking ash. Since then, a generation of scientists has watched, measured, and wondered if or when St. Helens might reclaim center stage in the chain of Cascade volcanoes. They placed sensors where no trees stood, sampled the regenerating valleys, and read meaning into every tremor and hiss. Now, researchers are observing signals from beneath the scarred summit that demand attention. The heat is emergent, rising steadily, not matched by dramatic earthquakes or visible eruptions, challenging the boundaries of current scientific understanding. What could it mean when this volcano, one recently suggested by new studies to lack the intense deep heat found under many of its peers, shows new signs of internal warmth? What is Mount St. Helens concealing in its icy heart? And, more importantly, could this be a warning? A mountain that shouldn't burn. To most eyes, Mount St. Helens is a monument to destruction restored. Wildflowers now paint its blast zone. Forests regrow inch by inch. Scientists champion it as a living laboratory, a rare chance to witness nature's rebirth on a landscape wiped clean by catastrophe. But the aftershocks of history still ripple beneath the mountain's fractured surface. The 1980 eruption, seared into global memory, was not just a local disaster, but a worldwide event. Ash circled the globe, with fallout reported as far away as Oklahoma. The blast reshaped physical and psychological maps of the Pacific Northwest. For decades, researchers described a strange paradox. Beneath most volcanoes, the Earth packs deep, persistent heat, a churning layer of magma capable of stoking eruptions centuries apart. Mount St. Helens, however, has stood out as an exception. Recent studies have suggested that the magmatic system beneath the volcano is notably cooler than those beneath neighbors like Rainier or Shasta, cooling faster and perhaps storing less energy for future eruptions. While scientists continued to approach the mountain with caution, many believed the risk of an explosive event was lower, the cycles more predictable. The legacy of 1980 was a tragic exception, not a rule. But the ground tells stories science sometimes can't. In 2025, those stories presented new chapters. Sensors embedded around the crater floor began reporting rising temperatures, subtle at first, then persistent. Where cold waters should have seeped, new warmth began to radiate, and where the subsurface was expected to rest, it now hinted at restlessness. Readings showed localized areas beneath the caldera that appeared warmer than at any point since the rebuilding of the dome. Surface observations matched what was seen below, and weekly teams repeated their checks, replacing sensors, reanalyzing data, and ruling out surface factors. But the numbers refused to budge. What does it mean for a mountain, long believed to have reduced volcanic fervor, to warm like this? Why would St. Helens, an anomaly among Cascade giants, display renewed subsurface activity? Signals from below. With temperature on the rise where models suggest it shouldn't be, the scientific instruments ringing the caldera flickered to life, not with drama or sirens, but with mounting certainty that changes were underway. The ground itself, scarred from the 1980 avalanche, sent subtle signals into every monitoring network. The advanced monitoring systems, installed and refined over decades of observation, had never seen this particular pattern. Faint, low-frequency tremors, barely perceptible, vibrated from the Caldera's underbelly. In years past, most recorded quakes occurred along known fracture zones or due to dome adjustments. These signals, though, differed, drawn out and pulsing in a manner unfamiliar to local experts. At USGS and partner laboratories, teams replayed the data streams, searching for classic earthquake spikes or the erratic signals of ice fracturing in spring. The rising heat came with a soundtrack of its own, one that didn't fit volcanic precedent. Meanwhile, gas monitors watching for sulfur dioxide or carbon dioxide noticed consistent, if minor, changes, enough to count as whispers, reminders. The mountain's subsurface chemistry is very much alive. What worried experts was not a single data point, but the accumulation of subtle, sustained anomalies, heat without major earthquakes, gas changes without visible eruptions. Together, they suggested forces moving beneath the surface. Even without a clear epicenter, was the mountain reliving echoes of its past or unfolding a new chapter entirely? At what point do scattered signals become a legitimate warning? And if history teaches us anything, can we afford not to listen? Ghosts of 1980. For those who study Mount St. Helens, every anomaly is colored by memory. The mountain does not exist in isolation. It carries the shadows of its own past. And the events of May 18, 1980, cast a long shadow over every new reading, every spike in the data. Nearly half a century earlier, subtlety was the enemy. Rumbling and swelling beneath the north flank went misunderstood, then underestimated. Jets of steam and tremors multiplied through March and April. But most believed the next eruption would be vertical. As volcanoes are supposed to behave, precautions were taken, but not for what really came. Then, without warning, the north face of the volcano collapsed, the largest debris avalanche ever recorded. The mountain's heart burst open, blasting sideways and unleashing pyroclastic flows that blurred sky and ground into a single searing moment. 57 people died before noon. Ash darkened the sky over Spokane and drifted for days across the Midwest. Rivers clogged with mud, landscapes were instantly remade, and memories forever altered by forces unseen until too late. That trauma of underestimating the unpredictable, of assuming nature would follow familiar rules, haunts every new discovery. As new heat rises, the ghost of 1980 returns to ask, have we learned what we needed to, or do we risk repeating mistakes? Patterns that defy explanation. Scientists are trained to look for patterns, matching new data against decades of precedent, searching for guidance and probability. However, the current heat anomaly at Mount St. Helens resists easy classification. It is, in a word, strange. Typically, volcanoes announce activity by ramping up in a recognizable sequence. Deep earthquakes signal magma movement, gas levels spike, cracks open, and steam and ash escape. In 1980, St. Helens followed this sequence, albeit all too quickly. This time, the story seems inverted. The earliest sign is thermal, steady, growing warmth radiating from below a caldera, presumed to be in the process of cooling down. The anomaly is not random, nor just surface level, but a trend sustained at multiple observation points. Other Cascade volcanoes, like Rainier and Hood, have signaled unrest through harmonic tremor or significant gas surges, but a quiet, persistent, distributed buildup of heat, occurring mostly without matching seismicity, presents a novel puzzle for monitoring teams. Ground teams and satellite sensors cross-checked and recalibrated, ruling out known hydrothermal processes, instrumentation glitches, or surface effects. Satellite flyovers showed temperature rises even in areas shaded or protected from atmospheric influence. Concern grew as time-lapse images revealed these affected zones slowly expanding. The heat pulse, instead of dissipating with time, appeared to be spreading out from a new source below. Old explanations, such as leaks from heat pockets or local friction, were checked and so far do not suffice. The data persisted, forcing the uncomfortable question: if not by familiar causes, then by what? What could drive renewed heat in a volcano believed to be cooling, and what are the risks when established models no longer fit? Evolving danger, unchanging uncertainty. As the heat spread, concern extended beyond the scientific community to local populations living in the mountain's shadow. If anything, the strangeness of the change made it more difficult to interpret and harder to dismiss. Every May 18th, the region remembers the catastrophic eruption, celebrating the return of life, rivers rebuilt, birds and bats returning, and wildflowers covering what was once volcanic ash. The landscape is a testament to resilience and recovery, but also to the need for vigilance. Now, uncertainty returned to the fore, an anomaly in the mountain's temperature, persistent yet unexplained. Emergency managers sharpened their preparedness, checking communication plans, evacuation routes, and siren systems that alert the valleys below in readiness, though careful not to provoke unnecessary panic. The challenge was not just the possibility of an eruption, but the lack of clarity about what, if anything, would follow. The mountain remains notorious for ambiguous warning signs. Was the heat a subtle sign of renewed explosive potential, a quirk of underground chemistry, or simply a false alarm? School children rehearsed Lahar evacuation drills. Scientists gathered to mark the 45th anniversary of 1980. Every conversation now colored by pressing questions. Seismologists compared this anomaly to events at other volcanoes worldwide, where precursorless crises sometimes ended quietly and sometimes erupted with little further warning. If Mount St. Helens was heating up for a reason science doesn't yet grasp, how would anyone know when or if to raise the alarm? The eyes and ears of modern science. If the years after the eruption were marked by trauma and rebuilding, the present is defined by near-constant monitoring. Since 1980, Mount St. Helens has become one of Earth's most closely watched volcanoes, wired for sound, vision, and every tremble invisible to the naked eye. Researchers track the pulse of the reborn ecosystem, even as their main focus lies below the ground. The mountain's rebirth zone has become a grid of probes and measurement stations. Every tilt, every subtle movement, every trace gas recorded and transmitted for analysis. Bird and bat activity is cataloged at dozens of sites, part of a major biological monitoring effort that echoes the scale of geophysical instrumentation. Yet ever since unusual heat was recorded, all efforts have focused on the mounting puzzle below the caldera. When the temperature anomaly emerged, monitoring intensified. Scientists compared multiple years' worth of baseline temperatures and scanned for historical parallels. Yet few explanations present themselves. Even advanced INSAR satellite radar, capable of detecting surface uplift as small as a few centimeters, found no marked deformation, just a stubborn, persistent rise in subsurface warmth. How much can observation alone tell us when the volcano's behavior defies current understanding? Paranoia or precaution? In the absence of more obvious warning signs, seismic swarms, columns of ash, or ecological die-off, a different crisis took shape, one of communication and of public trust. Emergency agencies debated what, if anything, to do. Was it time to raise the alert level, to warn communities nearby? Or would such an action spark unwarranted fear, disrupting thousands of lives over a mystery with no precedent? Because for now, there are no clear, ground-shaking quakes, no obvious deformation, and no sudden die-offs, only rising temperature and persistent uncertainty. The memory of 1980 made this a heavy responsibility. Then, evacuation came too late for some. The eruption misunderstood. Would officials now risk credibility over a heat anomaly? What guidance can they give the public when the science is as ambiguous as the mountain itself? Sirens and drills essential though they are, can be met with skepticism and fatigue when threats are not present or tangible. Social media filled with debate, rumor, and distrust. Some questioned whether this was just another dry run, or if officials were overreacting in the aftermath of historic trauma. Experts argued among themselves about communication strategy, whether to opt for full transparency or caution and restraint. Unexplained heat is not a prediction, yet it cannot be fully ignored. In such uncertainty, even small signals can take on outsized importance. When does vigilance become alarmism? The line between caution and complacency is thin, and history weighs on every decision. A clock or just a coincidence? As spring turned to summer, the pattern of the heat pulse drew attention for its persistence. Scientists noted possible cycles or rhythms in the data, distinct peaks and troughs, as if the mountain itself were responding to deep, regular forces. Theories circulate. Was the pulse an indicator of renewed magma movement? Could it reflect shifting groundwater systems? Or was it an illusion of pattern, a human tendency to find rhythm where there is chaos? Researchers mapped the anomaly against earthquake records, known volcanic cycles, and meteorological shifts, but no conclusive link emerged. The specter of past volcanoes, a reminder that sometimes the only warning is a pulse or a signal missed, haunted every discussion. Layers of fear. As scientific scrutiny intensified and local authorities reviewed emergency plans, unease crept beyond research offices and into the communities below. The public, long reassured that St. Helens had spent its fury, found itself worrying anew. Media coverage focused on both remembrance and risk. Headlines asked, "Unexplained heat at St. Helens. Are we missing the next warning?" City council meetings filled with questions as uncertainty lingered over why the lahar drills had suddenly become more urgent. Some in the public sought answers online, but the web offered only partial reassurances or stoked the embers of rumor and fear. For every reasonable doubt, there was a whisper of paranoia. The line between trauma and preparedness, skepticism and vigilance grew ever thinner. And all the while, the mountain's internal thermometer appeared to climb upward, indifferent to human concern. Is the public's fear simply an echo of past trauma, or are they responding to genuine, poorly understood risk? With the facts themselves uncertain, perhaps it is both. The hidden cost of not knowing. Within the research community, there is a quieter cost to uncertainty. To be responsible for public safety, but unable to provide clear answers, is an anxiety no data can resolve. The burden is especially heavy for those who dedicate themselves to understanding and communicating volcano behavior. Each unexplained anomaly stresses credibility. Every false alarm chips away at public trust. Scientists know their best models and tools are only as good as past experience allows, and that volcanoes, above all, resist easy prediction. Still, research continues, not only on the geophysical side, but also in the living landscape. The ongoing monitoring program samples birds and bats in dozens of sites, using them as sentinels of environmental change. Researchers find patterns in the recovery of wildlife, even as they wrestle with more uncertain trends beneath the ground. The lesson of 1980 was humility, never to underestimate an old threat, nor to assume the rules are fixed. Now, humility is mingled with frustration. Preparedness is only as good as prediction, and prediction is fragile when threats operate by unfamiliar rules. If Mount St. Helens can heat without quaking, change without warning, who is to say what will come next? The edge of the unknown. As the season advanced and the anomaly in temperature persisted, the scientific community stayed focused, their vigilance matched by a sense of awe and uncertainty. There were no sirens blaring, no columns of steam, only the slow, persistent rise of numbers marking the heat beneath the caldera. It is this, perhaps more than any visible eruption, that focuses the mind. Mount St. Helens is paradoxically both one of the world's best understood volcanoes and one of its most unpredictable. The cascade of scientific insight is matched by mysteries still unexplained. How much can instrumentation and monitoring deliver when nature writes its own rules at depths no wire or radar can reach? The world watches, marking the days since the last catastrophe, aware that uncertainty is sometimes the best warning they will ever get. What does it mean when the old threats return, not in violence, but in a quiet, persistent shift that defies understanding? The story is still being written. Under wildflowers and regrown forests, the heart of Mount St. Helens pulses, changed but never fully at rest. And so we watch, measure, and perhaps, above all, remember. Sometimes the most important warning is also the hardest to recognize.